Right, so implicit derivatives are required. You need to understand them before we do the word problems. So the entire section 3.6 is word problems. So you're going to be creating you'll have to create the equation yourself based on what they're talking about. And then you have to take derivatives of that problem that you made yourself. And those, so it can be difficult. You have to really know the geometry of what's going on. To try to visualize the problem. So it might help draw a picture, try to understand. And if you don't remember your old school area, volume, all those formulas, I would just, Google basic volume formulas, or if you want me to send you one, I will. It's not a big deal. Just have them ready, because I'm not going to force you to remember all of them. I hope you know them all, but it's okay if you don't. Like, do you guys remember the equation for volume of a sphere? Man, that's okay. So just have that type of stuff ready, right? Anyway, so let's review. Implicit real quick. Differentiation. So quick example. Take the derivative of the following with respect to time. So this time I'm not picking any particular variable that's in the problem. I'm picking time. So x squared plus 3y squared equals 7. So notice how there is no t for time anywhere. But you're going to assume that each of these are affected by time. So take the derivative with respect to t. So what you're going to do is take the derivative implicitly of both sides, or every single term if you prefer. So that would give us a derivative with respect to time of 2x squared plus derivative with respect to time of 3y squared equal to 0, because derivative of any constant with respect to anything is always going to be 0. So what is derivative of 2x squared? So then be 4x and then times the implicit piece. So it'll be 4x times dx dt, right? Plus derivative of this guy.
6y. dy/t, or we'll put it like that.
Yeah, dy dt. Exactly. So see how now it's implicit for the whole thing. Last time it was just, we'd have one of the derivatives would be fixed there, but now it's not. Okay. Oh, it's a mouse. I was like, what the hell is that? Where the hell is that not equal to come from? It's not on the paper. It's a little pointer. Confusing the crap out of me. Okay, so you guys remember these ideas about implicit? Is that clear? Because this is important before we start 3.6. Right? So this right here, with respect to time, right? So let's make some extra problems here just for fun. Respect to x. So d dx. Right, what would be our answer? Right, it should be similar. Get rid of this guy. Right, it's going to be just the 4x, right? So this will be 4x. So no implicit piece because it's matching the variables, right? Dx and x are the same. So you do it like you always have. These do not match. So you'll get 6x, or 6y rather. dy dx. Okay, so that's what we did last time. You guys remember? So respect to y would simply be amount of space. I'm just gonna move it over here. This guy would now be implicit because it doesn't match. This one would not be. So it would be 4x dx dy plus 6y equal to 0. You guys see the pattern, right? Any questions on that refresher for implicit? Okay, well, let's start some, before we get to the weird word problems, let's do some basics first. Homework starts off pretty chill, and then it gets difficult. You guys cool on this page?
Like with the respect to sign part, that's where we come up with, or not come up with our own equation, but this would, we have to make our own implicit things.
Yeah, basically everything is just treated as implicit
Okay.
because like if x and y represent something and it's all happening in real time, then they're all going to have their own separate rates instead of just one rate. Yeah, we'll talk about that real soon. First example. Problem 1, I think. Let me open the homework up. Make sure it's. All right. So example, problem 1. So assume x and y are both differentiable functions of time, t. Find the required values for dy dt and dx dt. So basically, we're going to take the derivative of both sides with respect to time. And then we're gonna plug in what they give us and find the missing piece. That's all we're gonna do. So it starts off pretty chill. We don't have, they're giving us the equation. Okay, just so we get used to it. And then eventually we will have to derive our own. Okay. So given y equal to square root x, find dy dt given x equal to 1, dx dt equal to 2. All right. The first thing we got to do is take the derivative of both sides. Oh yeah, thanks. Take derivative of both sides with respect to time. So this guy will become derivative of y is 1 times dy dt. Derivative of this guy, right? We should probably change that to a 1/2 power, bring the half down. You agree that it's going to be this, right? Let's skip the minor step there. Is that okay? That this is technically x to the 1/2. So derivative says bring the half down, subtract 1. And then the implicit says times dx dt. Is that derivative okay? Okay. So far, you guys okay? So at this point, they want dy dt, right? So just plug in the 1, plug in the 2, and that's it. One second. So once we do that, we'll know what dy dt is. So x is 1, so 1 negative half times 2. So that will be 1, right? 1 to any power will be 1. 1 times a half is half. Half times 2 is 1. Any questions on the derivative? Again, it's the same implicit stuff we talked about last time, right? You see, once you do that part, you're just plugging in numbers. So given dy dt is equal to 8 and x is equal to 64, find dx dt. So we already took the derivative here. Where is it? There. So we can use that there as a starting point. Right? So just plug in everything we need and we'll be good. dy dt is equal to 8. X is equal to 64. We need to find dx dt. That's a half the power, by the way. So what does a half power, negative half power mean? What's that? Yeah. We'll be winning. The reason it's going to be an 8 is because this goes to the bottom. A 64 to the 1/2, which is a square root. So then 8 is equal to 1/2 times 1/8 times dx dt. Anyway, we got a 1/16 there, right? So multiply both sides by 16 and we'll solve for the answer. At this point, we're just doing basic math, right? What's 8 times 16? 128? Yeah, okay. That's all they want. Anyway, you see what we're doing, right? We're just plugging in the numbers, solving for this piece. Because once you have the derivative, the calculus part is done, and we're just doing algebra. Plug in the pieces, solve for the missing piece. Any questions on A or B?
So I think we use the same one.
Yeah, it's the same because it's the same derivative with respect to time. So if they ask for dx dt, you would still have to do that same derivative anyway. So we're just using this guy right here. We're using that twice.
Those are like when they say x4, x1, those are different points in the graph.
Yeah, or could, like if it's a real life problem, like that could be like distance or like height or something. It depends. So this 8 right here, this represents the rate of y changing over time. And this would be some height, some measurement, some moment.
See the graph like it's going
Yeah, like for example, if we had a, I don't know, I think there's a example we're gonna do later. We have like a ladder falling down, right? So what's the rate of the changing x? So if there's a, you have the ladder on the wall, and it makes a triangle, right? So as the ladder falls, the height of that wall is shrinking as as the ladder falls. But the ladder itself is fixed. So you have a changing rate for the y-axis, and then you have a base that doesn't change, and a horizontal that doesn't change. It's called hypotenuse. So depending on the problem, different things are changing. Or if we have a balloon that's being pumped up with air, radius is changing. So that would be a dr/dt. Volume is changing, so that would be dv/dt. So stuff like that. So it all ends up meaning something.
By the equation, then whether it's going to go like a slope.
Yeah, I mean, this tells us that it's some sort of increase, but since they didn't tell us any details, it's still in general terms right now. But all we can see that this is increasing, and so is this one. So when x is equal to 1, this is the rate at that size or input.
Positive, that would be like the y.
Yeah. This is positive. It's increasing. All right, let's move on to example 3. It looks a little harder. It's similar to what we did earlier, actually. Let's do that guy. You guys cool on example 1? Is that okay? So let's do number 3 implicitly again with respect to time. Okay, so given x squared plus y squared equals 169. Part A, find dy dt given x equal to 5, y equal to 12, and dx dt, so this rate of x equal to 5. All right. So take the derivative of this guy with respect to time. So ddt of each term. So get rid of this guy. No big deal, right? Which is 2x. And then you add the implicit piece. Derivative of x with respect to time. Because I'm doing a t, this is not a t. Derivative of this guy is a simple 2y, and then you tack on the implicit. dy dt. 0. So once we're just going to use this guy to answer both parts A and B. Okay. can plug in all the numbers now if you want, or you can solve for this piece. I'm sorry, this piece first. Doesn't matter.
So then we don't have to simplify it, right? We can just plug it in once we get the derivatives.
Yeah, you can plug it all in right now. You just need to isolate this at some point. So isolate it in general or isolate it after. Doesn't matter. I'm gonna subtract this piece over there. I'm gonna do it in general. Divide by 2y. And I've solved for the piece they want. So I'll go ahead and plug it all in. So x is 5. Now these 2's are gone. X is 5. Y is 12. This is 5. So 5 times 5. That's it, right? That would be the answer. Any questions on part A? You guys good? Okay, let's do the next part B then. X is 12 still? No, actually, they're opposite. Y is 5. dy dt is -5. So start with the same piece here. Let's solve for dx dt this time. So there we go. Let's subtract this over here. Divide by 2y. 2's are gone. Plug in your x and y. So that'll be -12 over 5 times oh shit. They wanted dx dt, right?
Yeah. Good.
My bad. My mistake. Okay. So solve for dx dt. So subtract the 2y dy dt. Divide by 2x. Plug everything in. And we'll have this here. Oh, I don't need the 2's. 2's cancel, I forgot. So plug in the 5. Plug in the 12. Plug in the -5. So this would be 25 over 12. Do you see the general idea? Right. So that's what you're going to be doing, except you're going to have to be developing your form, using the formulas and developing your own equation full of derivatives. So all these steps will be the same. The hard part is just choosing the right formula and then taking the derivative appropriately.
So I can do negative time.
What's that?
I can do negative time.
Well, we have a negative rate. So this would be, the time would be positive. So over time, it's decreasing. So like if I was, I don't know, emptying something out, that rate would be negative, but the time would be positive. Does that make sense?
Previous one, for A,
Yeah, that's.
A is negative.
Right. So this is a negative rate. But it's, so you're losing over something over time. So time is still positive.
It's not the time itself we're talking about.
Right, it's a rate. So the rate of y over time, the change in y over time is negative. The time itself is not negative.
So the final answer for A is the rate of y over time. Final answer for B is the rate of x over time.
Yes, change in x over time. Yeah, change of time. These guys here. That's what we're taking to with respect to time, because we want to know what's changing over time. Okay. Now they mean something specific now. So let's do an area problem. You guys cool on this big page? Sorry, one moment. I think this is problem 5. Let's see. Yeah, so check this out. A radius r of a circle is increasing at a rate of 3 centimeters per minute. Find the rate of change of the area when the radius is 37 centimeters. So they're not giving us anything. We have to develop the equation ourselves. So at first read, it sounds challenging, but it's not. So what's changing? Yeah, so the radius r is increasing at a rate of 3 centimeters. So do you agree that that is dr dt? Right? Change in r over time. they want us to find the rate of change of the area. So they're talking about the area of a circle. Do you know what the area of a circle formula is? Back,
Pi r squared.
yeah, pi r squared, right? Okay, so let me just switch back. I'll come back to this in a second. So area of a circle is pi r squared, right? They told me that the radius was 37, is that right? 36. Yeah. And the change in radius over time was 3 centimeters per minute. So they want to know the change in area. So do a derivative of A with respect to time. So dA dt. D dt of both sides. So this guy would become dA dt. No big deal. What would be the derivative of the right side with respect to time?
Two pi r.
Yeah, it'd be 2 pi r dr dt, right? So we have the derivatives now. They want us to find the change in area over time. So they want us to find what dA dt is equal to, given this current radius and this current rate. So plug this garbage in, and we'll have our answer. So the change in area over time will simply be 2 pi times the r times the dr dt. Okay. They wanted to keep it in pi or not? Yeah. We'll keep it in pi units. So what's 3 times 37 times 2? 222? 222. What would be our units? Right, we're dealing in area, right? So it would be the change of area squared, so centimeter squared per minute. So every minute, the area of the circle is changing by this much. Given this rate of change on the radius. So as the radius grows, right, the area of the circle is changing by this much. Any question on this? See how useful this is, right? It's not just random stuff anymore. A lot of this stuff will come up a lot in engineering. I think when you get to differential equations.
What's so about how long will be the board?
Yeah, that's true. Like if you had you're pouring and then you knew the radius growth you could know the area of the pancake. It's true. You guys taking physics yet?
Your
I
class
have
is
to do
required
that.
for it.
It's not required?
And
No, your
yeah,
class is required for it.
Oh, Cal 2?
Yeah, you can't take physics until you take calculus.
I think they allow concurrent, but not. I don't, at least they used to.
they
Take
were
one,
gonna let me do it,
you asked them?
yeah. But I had to take physics this summer.
I see. And I mean, they let me do it back in the day. But guess it's changed.
Good because I have a full-time job too, though.
I mean, I wouldn't recommend it. It's hard. Physics, engineering physics, or whatever it's called. University physics. Yeah, I think that's the name now. That and calculus at the same time is a lot of work.
I had to do that and Cal 2 at the same time.
That's even worse. No, no. I mean, I can, but I don't officially. No.
Want to do it this summer?
No, I'm not allowed to. To teach a topic, you need to have at least 18 graduate hours in that subject. I don't have that many. I enjoy the topic though.
So waiting on put you in the Cal 2 rotation this summer.
Yeah, we'll see what happens. Is it still blank?
There's still not that many doing it this summer.
Let's do the sphere. That one's interesting. So the radius of the sphere is increasing at a rate of 3 inches per minute. Okay. Find the rate of change of the volume. All right, so what is the 3 inches per minute? We have to be able to recognize what this garbage means. Yeah. So the change of radius over time is 3 inches per minute. So dr dt is 3 inches per minute. Okay. What's the formula for a volume of a sphere? Yeah, I believe it's 4/3 pi r cubed. Now let's double check. Let's use the Google machine.
Volume of the sphere?
4/3, yeah, 4/3 pi r cubed. Okay. All right, so the question said, share the screen. Okay. Question said, find the rate of change of volume when R is 11.
So in this case, it would be d over dt, right? For the volume. D
Yeah.
equals 3/4.
So take, yeah, exactly. So take derivative of both sides with respect to time. And then we're going to use that R. Let's go and do the derivative first, I guess. What would this derivative be?
Four pi r squared.
4 pi r squared. Don't forget about the implicit. So part A says find the change in volume when your radius is 11 inches. Shorten that up to find dv dt given r is 11 inches. Okay, so plug it all in. So dv dt is equal to 4/3 times pi times 11 inches cubed. What is 11 inches cubed? Times. Wait, hold on.
1,331.
My bad. I used the wrong formula. Squared. It's 121, right?
I got 1,452.
For squared? So that's,
Squared.
21.
let's see, times 4. Should be square. I was using the wrong one.
One's a pair here.
Yeah, so remember, we're using dv dt. Let me fix this for you.
Right back to the original.
Yeah, so 4 times pi times 11 squared times dr dt. There you go. Okay, so that'll be what, 12 times 121? What's that gonna be? You said 1452? That sounds familiar.
That's what I got. Just cubes.
Inches cubed over a minute. Yes, they got. I'll leave some for you. Let's look at the schedule. Let's move on to 3.7, I guess. You guys cool on 3 and 4? Three point seven, like I was saying earlier, it's pretty chill. Okay, so this section is really just about formulas. I think I sent you guys a page of derivatives, right, a while back? Formula sheet.
Do something, let us be able to see 3.7.
Probably, yeah. One sec. Yeah, I don't think it's published, right?
Thought you did, but it's not on the.
So, me.
Still a little bit.
What's it saying?
I can see it now, but it's not. I can see the instructor videos.
Did you hit refresh?
Maybe I gotta hit that.
Yeah, that's true. Okay. I sent you guys a formula sheet. Picture. Okay. So the derivative of arcsine is going to be equal to this. Let me find a simpler looking one. Yeah, this is fine.
That sheet for test.
Yeah, that's fine. Okay. So whatever x is in here, will go inside the x squared. That's all you gotta do. So we have inside the argument, we have x minus 3. So the derivative with respect to x, excuse me, is equal to right? Formula says 1 over 1 minus x squared. So 1 over square root of 1 minus x squared. So literally, that's all you're doing. You take that argument x, x being the thing in parentheses, and you plug that into the bottom. So the derivative sine inverse, or arc sine if you prefer, is 1 minus x squared minus 6x plus 9. Which will be 1 minus x squared plus 6x minus 9. Which will be negative x squared plus 6x minus 8. Anyway, that's good enough for me. That's a quick note. Arc sine of x is equal to sine inverse of x. It's the same thing. I'm sure we talked about that in pre-cal. It's different notation. I like the arc sine better because it's clear. This could be a power. Whatever. Any questions on example 1? Do you see how we're just using a formula? Well, there's technically a chain rule happening, but it didn't really matter here. You technically should be multiplying by the derivative of the inside, but the derivative of the inside would be 1, right? So it made no difference here. So the formula should be times the derivative of x, like to make it more general. Like this guy, where is it? This one. This is generalized. Share the screen. Right. Derivative of this guy will be the same thing times the derivative of u. So this is the chain rule up here. Okay. I don't know if the formulas I sent you had that part on there or not. I'm not sure. But just remember that if you see a complex argument inside the inverse function, that you may have to do a chain rule. This one right here. Look at the homework again. So that was number one. Let's do three. So problem three. Okay. So the derivative of this guy will require that formula. That three is whatever. I'm gonna give you the formula over here. The derivative of our cosine is equal to derivative of x over negative over the square root of 1 minus x squared, where x is the argument of the inverse function.
Sure.
Yeah. So this is the formula that I showed you earlier. So x is this argument. Take the derivative of the x, plug in the x here. That's it. So derivative of this guy will be, I'm gonna ignore the 3 for now. Doesn't matter. So negative x over 7 derivative over square root of 1 minus that argument squared. The derivative of this would be 1/7, right? So that'll become a negative 3/7 on top. Just follow the formula. You see how x prime is derivative of the argument? This is 1/7 times the 3, so negative 3/7. Down here we have 1 minus x squared. That x again is the argument, so x7 squared would be x squared over 49.
And then arc cosine, we're taking the derivative of that because it's considered a complex one. It's a fraction. So we're saying.
Yeah, it's just a chain rule. Yeah. So because that argument is a little more complicated, you're required to do a chain rule. But it's better to just think of it as always being there, the chain rule. So that way you won't miss it. So most of the time that chain rule will be a 1. But times like these, example 2, it won't be.
like on that example one, because it said arc sine x minus 3.
Yeah, so
So
they're
I
the,
would just put a 1 there.
yeah, yeah, so I'm saying like it'd be better to have use the other formula and just say, you know what, this is x minus 3 derivative. And then you get to here. That way, even if it doesn't matter, you'll never miss it. But anyway, it's just going to be that formula over and over again. So look at your formulas for sine, cosine, tangent. Should be good. But let's do a couple more just in case. You guys cool an example too?
Why wouldn't you multiply the 7 by? Instead of just doing the x.
The 3 by,
Numerator?
yeah, I did. So that's why it's 3/7.
No, it wouldn't be 3/21.
It's 3/1 times 1/7. Because 3 is a whole number and the 1/7 is not. If it was 1/3, then yeah.
And so that's also why it doesn't mess with the bottom. That's why you don't have to multiply the bottom 7 by the 3.
Um, yeah, technically it's this. So I only put the 3 on top. You could also rewrite it this way if you prefer. Oops, that looks confusing. Hold on a second. We could write it that way too. Just put 7 times this.
But it's either one of the final answer.
Other one is fine. Then you could subtract those fractions if you want. Make it a little prettier.
This is another section where all the answers and you look up.
A little bit, yeah. I mean, we could try to make it prettier by forcing that 7 inside. Doing some witchcraft. Right, because if I bring a 7 inside of roots, it becomes a 49, right? You agree with that? Then I can multiply that in there and get something prettier. What? See, that's kind of, it's a little nicer, right? No? Man, it's better. Slightly. Keep polishing that baby, man. Put some lipstick on it. Could rationalize, get rid of the root.
Let's just go back to like the first one.
So that's the last thing we could do, but you see how that 7 went in, all right? That makes sense, that logic. I'm not saying you have to do that, but do you see why that works?
Yes. So if you pull, if you square root of it, you pull out.
Yeah, exactly. So if I do the opposite, it'd be a 49 going in.
Oh, okay, now I get it.
Reversing what we would call.
Yeah.
Not gonna do it.
But it's kind of cool how they canceled that 49 though, right? It's kind of nice. almost like it wanted to be pretty, but whatever, didn't happen. Okay, so those formulas are all you really need. So make sure you have those at the ready. Any other questions on 2? Okay. Do one more and then we'll move on to something else. There's time or not. But yeah, if you look at the formulas on that sheet, all the derivatives, almost all of them have square roots built into them. So they're not very pretty to begin with. Okay. Okay. It's a e to the 3x. Looks like a weird 3 there. Times arc sine. So what type of derivative do you think this is? Yeah, it's going to be a product rule, isn't it? During the product, we will do the inverse derivative for arc sine. So g prime is going to be the derivative of the first one times the second one plus the derivative of the second piece times e3x. So what is the derivative of e to the 3x?
3x.
And then the chain rule? Right, we have a 3 up there.
3EX.
Yeah, 3x. Okay. Arc sine is just chilling there. It's cool. Derivative of arc sine is now the new form as we just did. So that will be derivative of the x, which is 1, over the square root of 1 minus that argument, which happens to be just x. So this derivative is just a formula. I think that's good enough. Who cares, right? No need to polish this turd. Any questions on this derivative?
I feel like you magically came up with an extra E3X.
Which one? This one?
Unless that just moved over. Is that what happened? The E3X that's on the side there just moved over next to the one.
This one went to here. Yeah.
Yeah.
Yeah, you multiply it.
That makes sense.
Okay, so the derivative of the E3X is 3E3X?
Yeah.
Okay, that's where I'm at.
Well, that's what you told me.
I said 3.
Okay,
So is that the final answer?
Yeah.
Okay,
we can do some polishing now.
no.
Just saying. Okay. I think that's enough of this formula stuff. I think it's pretty straightforward. Just remember what the formula looks like and how it works. Let's see how much time we got. Yeah, let's do one more section. You guys cool on problem 4? Or sorry, example 3, problem 4. Next section is pretty short. We might as well just get it out of the way. Since on Newton's method. This method is meant to be programmed because it's an iterative method to approximate a solution. Here, let me put it in English. So if x sub n subscript is an approximation. Approximation is 1p, right? Or 2p's. 2. I feel like that's right. Approximation. Let me write that better. Of a solution of f of x equal to 0. And if f prime of x sub n is not equal to 0, then the next approximation is given by this formula. So x sub n plus 1 is equal to xn minus f of xn over the derivative of xn.
So that was x n plus 1.
Yeah, x subscript n plus 1 equal to x sub n minus f of that xn over the derivative at xn. So basically this is saying that the next value is equal to the previous one minus the function at that value divided by the derivative at that value. So this will actually help you find zeros to a function. Which is probably what your calculator does when you tell it to approximate zeros. You know what I'm talking about? But it'll find the intersection or 0, depending on what you're doing.
Yeah, my calculator lost me.
I have no idea what you're talking about.
Well, I think I have one somewhere. Basically, what I'm saying, if you had a semi-fancy calculator, not super fancy, but also super fancy, either way, or
The appeal
Why? Well, it depends what the function is. I don't know, just make that up there. So, I mean, math is always very general, right? So we've been doing derivatives for no reason until recently. Now they actually mean something, right? The same thing with zeros. You did that a ton for, you know, probably a couple of years. Doesn't mean anything until you decide to apply it. An example could be, let's say you're doing a physics problem and you want to know at what time my projectile will land at that ground point. So the zero in that case would be the landing spot. So you can calculate the time of when that's going to happen. So you can create all kinds of applications. But in general, it doesn't really mean anything, right? But it can. If these are profit functions, we might want to find intersections or peaks or maximums. We might want to know when we're going to zero, when we start losing money, right? Because after that zero could be a problem. We want to know when that happens. Or if it's the opposite, right? If we're in the red and we're making money, when do we break even? That zero would be a break-even point. So
This is when all those people wondering, when am I ever gonna use this in real life? Need to get to.
yeah, it all means something. Just depends what we're talking about. But- No, I know. I didn't assume you were, giving me crap or anything. But I do understand what you're saying, though. Math people are very general, but there's always an application. But anyway, yeah, it does give more motivation. It's true. So these zeros can be found with the Newton's method. So a computer program, calculator, will figure this out. Like we'll figure out, okay, well, given some initial point that I choose or that I'm given, I can keep doing the method until it approximates closer and closer. And how many times I iterate the process. So if I was doing a program and I tell the program to loop 100 times or 1,000 times, it'll get closer and closer and eventually it'll give me exactly 2. Right. So that's what this guy does. This formula form. It'll find that. But of course, we're not robots. So we're not going to do that 100 times because that would be stupid and very frustrating. So I'm just going to show you how to do it a couple of times. We'll just let it go and move on. Okay. So first example. Calculate. Two interactions. Sorry, two iterations, my bad. Two iterations of Newton's method. Okay, I picked this one earlier. There's a function. Calculate iterations to find the zero, given an initial point of 2. Obviously, the derivative would be 2x, right? Okay. So it says 2 iterations. So I need to find x2 and x3. So x2 is equal to x1, right? As the formula says. So the next point is equal to the previous point minus the function at the previous point divided by the derivative at that point. So that will be 2 minus f of 2 over the derivative at 2. Does the notation make sense to you?
So we would solve 2 squared minus 5 for the top and then 2 times 2 for the bottom.
I'm sorry, one more time, sorry.
We would solve 2 times 2 squared minus 5 for the top
Yeah,
and then 2.
yeah, exactly. You're right. So plug in the 2, plug in the 2, right? Okay. Is that garbage gonna be 4 minus 5 over 4? That'll be a negative 1/4 minus 4, so 2 plus a fourth. Right? 2.25. Uh, iteration? What does it mean? It's an easy way to explain it. So an iterative method is like a repetitive process. So it means I'm doing it in iterations, meaning like it's multiple attempts.
Oh, you were saying 400 times.
Yeah, so I'm only gonna do it 2 times. I'm not gonna do it 100 times. So instead of cranking out doing that formula that we just did, so the calculator would do this for us, right, in the computer. So they'll do all this calculations 100 times and then get this answer, plug it back in, get the next one, plug it back in. It'll keep doing that until you tell it to give you a tolerance. So if you're coding it yourself, you'd say, all right, keep going until I get, I don't know, the thousandth place or something, right? If you're familiar with programming, you'll see that repeating itself, you have to give it a limit, either a number of loops or runs or iterations, or a tolerance to tell it to stop when it gets close to the 0. So when it's close, so assuming that the 0 is, let's say, the number 2 or number 5 or whatever, when it gets to 5.0001, that's close enough. You tell it to stop. So that's one iteration. That was one step. So repeat yourself the second iteration. Pretend you're a robot. So now I'm going to plug in x2. See how this is going? So this will be 2.25 minus f of 2.25 over f prime at 2.25. So 2.25 minus 2.25 squared minus 5 over 2 times 2.25. So at this point, it's time for some calculator. What is that going to be?
Final answer would be 2.24.
2.24. I think you're right. Let's see. I think I did this at some point earlier. Oh, no, I did.
0.237.
2.25 times 2.25 minus 5 is 0.0625 divided by 2 divided by 2.25. So yeah, I got 2.24, is that what we said? Yeah, it's rounding. Well, they got to tell us what to round to, but 2.23611, what's what I got? So as you can see, it's getting closer and closer to something. If you do this 100 times, if you're really bored, you'll find the zero, right? Eventually. Eventually, it'll stop changing very much at all. It might change in the like 10,000ths place or something. So anyway, any questions on that? Do you see what the method does? Let me open the homework so you can see it real quick before we call it a night. So in the homework, they have you do this piece by piece. They don't do it all at once like I did. So basically, they're going to say, all right, well, what is, if xn is the general term, x1, right? 1 right as n right here would be the first term. So that's given to us. So you just plug in a 2 here. Then it says, what is a function at x1? So plug in the 2 in here. We got -1, right, on the paper. Plug it into the derivative. 2x, it'll be 2 times 2, that's 4. Divide this guy by this guy, we got -1/4. Altogether, we got 2.25 on the paper, right? We did all this at once, and we got this answer. They did it piece by piece, just cuts. So I'll let you do that on your own. But
Video that I can-
a video of what?
Video examples, the questions, they're better to watch.
Might be, I'm not sure.
So,
But you see how you understood the whole thing though, right? We did this piece. So if you look back on the paper, f of xn, all that is it's this piece, right? F of xn is f of 2. So that was 4 minus 5, which is a -1. So the -1 would go there. F prime of 2, we got a 4. So that 4 would go in there. Dividing them together would give us a 1/4. The final result was this. So they just did little piece by piece instead of doing it all together, which I think makes more sense, but whatever. Any questions on the Newton's method? You see, it's just a formula that requires many steps to, increase accuracy. Is that okay? We'll stop here. We're out of time, but the rest of the homework really is the same thing. So yeah, do 2 iterations, it just repeats itself. Number 5 is the only one that's slightly different. So instead of finding a 0, they want you to find an intersection. So what you would do is set them equal to each other, and then set them equal to 0. So subtract them, and that'll be your f. So it's the hint right here. H, you're gonna be using this guy to do the minus and use that as your H or your F function. So you know how before we had some F there, they gave us x squared minus 5, right? On the homework, the first problem we did. So this problem right here, that's the F that we're using to in the method, right? So the only difference for that question I just showed you is that their F is actually the difference between this guy minus that guy. Use that instead. So that'll be the only difference. But everything else will be exactly the same. Just subtract them before you start.
You also just graph it.
If you could, if you graph both, you could use Desmos to approximate. Desmos might be more accurate though, because we're only doing what is it, 2 steps or maybe 3. So that might be an approach you could use. Yeah. Curious now. 2x, right? Plus something. X plus 9. What was the other one? Something. Plus 2. Point 545. 0.545. So kind of. I don't know if we'll take that other answer. Anyway, I guess we'll see you Monday. That's pretty much the end of chapter 3, which means we'll have a test soon. So we'll start reviewing next week. We'll figure out a date later. I think it's time to go home and rest.